Good morning.
Good morning.
How are you?
Okay. Um, I'm trying to think of some other things than yesterday that are new to say, but it's been a very interesting week in terms of making foundational developments and moving some things forward. So um, I know there's probably a lot of cool things to talk about today. I know, I assume you want to talk about the philosophical transactions paper.
Yeah.
So I look forward to that discussion very much. And some of the things in the issue too, I haven't really gotten to. I haven't had a lot of time to sit and read everything in that article or that volume or release yet. But it's been interesting to see both Levin stuff, Benjamin Lyons there, who was someone I actually met in person at the OGLAB Summit last year. Comes to the Ecolopto community. We had the Ecolopto community salon wrap language computational stuff Wednesday or Thursday. I think it was Thursday of this week. And I've been thinking about that event still. I actually wrote a piece that not really totally germane to this lab, but a small essay for another project that I'm working on that mentioned all of those things. So that was a recent. You know, sometimes you're in a state of development of ideas, and you know it's going to be everything's so primed you can just easily write something else that's sort of adjacent to it. That kind of happened also yesterday, in spite of other much bigger, the hard and really heavy the things aren't usually that way. at least for like the things you like that are the really things that are really blocking everything else, tend to not necessarily be that way. So I kind of had a fun treat of reflecting on all that stuff and spitting something out. But that's sort of what that actually did happen between the last time we spoke. But yeah, the transaction the paper series is out. I want to read some things about more of some of what Adam Safron wrote there. Obviously, Levin's got a bunch of things coming out as always. Benjamin Lyons is doing interesting stuff. I think he's. It's been interesting to kind of see his stance and his evolution of his work with like both Lisa Feldman Bear, and he wrote one of the papers with Michael Levin proper, and he's collaborated with them for a while. So lots of interesting things there. I'm sure we'll get to, and I'm hoping. I don't think data and direction folks will start proper coming here, at least for another week or two. But should any of them be watching who applied, just very impressed in both the quality of the applications, but also the not just like oh, you're well qualified, but I it lends a very particular sense of responsibility in my end that what I've tried to tailor the internship and the program towards is something people are recognizing they want to do, and I want to try to make the program as good as it can be, because people have found it, and people have some people have gone very much out of their way to find it because they're looking for it on purpose. So it's kind of an interesting time to be not super published or not super publicized and not super well known about something, because it seems to have tailored a lot of the it seemed to have done a lot of work that last year did not did not do the same way. So excited for that. I have many emails and applications to like still reply to in E2, but I'm hoping in the next week or two that will start officially. So that's my opening speech.
Well, good. Yeah, that was I think a lot of good things going on there. And it was a good meeting yesterday. A lot of things that came up. I'll talk about that in a little bit. I don't know if Morgan had anything yet. If not, we can move on to the meeting for open source. So this week we did not have a DevaWarm meeting. We did have an open source meeting yesterday. So our open source meeting was yesterday. We had, I think, Hough was there, Kewen, Chen was there, Jesse, Morgan, and myself. And we had a nice discussion on different things in open source. We had discussions on project management. We were talking about the JoePro website, and I had brought up that it's that's something that we don't really think about with projects, is the not just the documentation, but the strategy for like kind of advertising what it is and what you're doing. So like with if you had a CV, a personal CV, you would have a list of publications. Those publications, of course, if you just list them as line items, it doesn't tell you very much about those things. It says, yes, I did those things, but it doesn't tell you a lot. It doesn't advertise things the way, say, a website would. And then a website, of course, you might be able to give more detail on things, links maybe to relevant videos or relevant excerpts. But for the most part, a lot of, say, academic websites are just that list of papers and just the line item of accomplishments. Now, that's one thing about like what we can do with our presentation of what we do. We could, maybe list a project and then get into a very brief description of what that project was or why it was valuable. And that's one challenge. So getting like that all boiled down to, something that's useful to people, something that captures people's attention. The other thing is keeping it current. So we oftentimes update things very irregularly. If you hire someone to do a website, as they say, it's usually building it, and then you don't really hire someone to maintain it so often. And so that's something that gets done haphazardly as things accumulate, and as a result, sometimes you miss things. And so I think it warrants a strategy for thinking about how to manage that sort of content. And this is relevant for projects too, because in projects you're making a lot of advances weekly or monthly or annually. You're giving sometimes an annual report, sometimes a quarterly report. But that's, of course, at the discretion of, it's at the discretion of the person leading the project. It's also maybe according to the mandates of like a funder or, just kind of convention. Like I give a quarterly update because I have to. And in that quarter, there's a certain amount of stuff that we did. And sometimes that, things leak across quarters. Sometimes they get kind of forgotten about during a interval that's maybe long enough that you can forget about things and that sort of thing. So it's really hard to really have a strategy for reporting out what happened in a project. Sometimes it's hard to even make a line item of something. So if you're making progress on something, that takes like 3 years to do, and you make progress on some project, you may often not report the breakthroughs as they happen because you don't know that they're breakthroughs until you're done with the project. and then sometimes you forget about those things in the process. So that development is not always documented. So and we
Yeah,
talked about that. Yeah.
I think that's a fantastic point. I don't think I've ever really made that point or heard it talked about. I'm sure you've alluded to it or mentioned before, but it never like clicked in my mind in the way that it has right now, which is so true. In that you don't like, there's, it's not quite the same obviousness and expanded timelines as like, you know, you write you have an idea, you write a paper, review the paper, you submit the paper, it gets reviewed, you submit the paper again, whatever, it gets blah blah blah, and then it's published. Like that's a very obvious iteration cycle, right? But internally, like, and this is like very internally, as you're developing the thing, it is quite the case that you may be making a you the inability to recognize the breakthrough in the moment that it happens in. And sometimes it's very obvious, but sometimes you won't know. Like you're kind of blazing the trail, and you're like, okay, you go down this path, and like, geez, this looks really promising, but I don't know, I don't have time to get into it. And you have to like come back later and then get the correct vantage point, which is an allusion to the sort of old essay I refound, the scaffolding of vantage points essay. You have to get to the right perspective and vantage point to see it, right? And that can be in the process of what Bradley's actually directly talking about. It's almost like, uh, it's such an interesting, I don't want to say outlier, but it's such an interesting component to, and that's why it's such an interesting component to the process of like trying to document, trying to understand where it goes, and then having, keeping your internal self even, or your team or your colleagues sort of on the same page as you're moving traversing this path. And then that's going to be totally different than anything on a website or a tweet. And I think that's partly why, for better and worse, and I would say some, maybe mostly for better, but like why things like, I wouldn't say micro content, but tweets and Substack notes and Substack posts and academic blogs have kind of, I think what they've moved towards is sort of capturing some of that. Not just because the whole, I was a little etched in my mind the first time some of the conference, like, a big AI serious, well funded conference, they were just saying, this is some years ago, but like, oh yeah, like we only have time to read the preprints now, not just because we're in the preprint, micro, like present shock preprint world where there's, you're not waiting for publications for a lot of things that you're building and doing, but just because, it kind of breaks down a little bit of the internal external barrier if you want to bring other people in line to it, to the discovery and the seeking, and actually, oh, it's actually a breakthrough process. But even with all those things happening, like the very personal, I would say, act of trying to explore, um, those spaces is sort of inherently, uh, you know, there's an inherent like total incongruence with trying to make something publicly intelligible to other people that aren't in the house. So I
Yeah.
appreciate the way you phrased that today.
Yeah, I think that's good. I mean, it seems a little, you know, in the weeds and not interesting, but it's actually quite important. So glad we had that conversation. Um, so yeah, and then Jesse gave an update. He talked about this cultural computing event in Ecolopto, and then talked about what we just said. That was that part of that discussion. Then Morgan, of course, gave an update on his work on open source. This is the stuff that he's been doing with agentive coding, and he was highlighting this repository on the anatomical compiler. So this was the previously he called this repo the organoid HGX benchmark. Now he's calling it the anatomical compiler, and just kind of going through, what it is. So basically, it's benchmarking data sets, or benchmarking some uh, data sets with code to, um, serve some of the needs of the experimental work that they're doing with organoids. So it's like going from an organoid to some of its biological markers to bioprinting for um, different types of bioengineering applications. So that's what he's doing. So he's building all of this in open source, and he was introducing that to everyone. So there's the idea is you can go from like a white paper to a data set to this code that then executes, and then you end up with this endpoint where you can do things like 3D printing or visualizations. And all of this code, of course, was generated with the help of an agent. So Morgan and an agent went back and forth. So I think this is a nice example of an open source project that is really interesting and really can be, you can look at the iteration of it and say, what are you learning from that process? Just as much as like highlighting the tool, because we do that a lot of times when we talk about open source projects. We just show the README and we show the tool and we say this is what it does. But of course, open source is about that process of development just as much as it is the end product that's open to people for people to use. And so, of course, with Morgan, he's using this agentive coding strategy where he has, I believe he's using Claude, and it's like, him identifying Claude's output when he prompts something, and then refining those prompts and getting the result that he wants. So there's a lot of domain knowledge there, of course. There's also a lot of hard work that goes into keeping the agent on track, because, you can query something from an agent, and an agent will give you something as output, and it has to make sense. But moreover, it has to be operable for what you want. Not, you're not always going to get the exact result that you want when you make a prompt, or you can't get the sort of the exact right prompt to get what you want. There's always this process of revision and a rapid iteration. So that's what we talked about. And then we also talked about this idea of pedagogy, or using agentive coding in edtech. And so this is a conversation I want to have maybe next week in this Friday meeting, is about what are the imperatives for edtech, or the imperatives of agentive coding in edtech. That's a kind of a personal interest to me, and it's also, I think, of interest to a lot of people who are faced with this problem in academic institutions where the administration really wants to use AI tools. And the ed tech people, of course, a lot of times will develop different tools, from sort of these trending technologies. And then people who say are instructors, or they have, like class projects, they want to apply those technologies to learning, but they want to make it effective, and they want to make it useful. And so that's the problem we have, I think, again and again, is how useful are these tools? Can we not just use them in say, a project context, but teach people how to use them responsibly and effectively, and that sort of thing. So I think that's a good thing to have a discussion on. And maybe we can even have a more formal discussion on its own about that at some point. Like, we can host a session where maybe we invite people from outside to come in and talk about it even. But I just want to get that ball rolling, because I think it's a very important topic. Okay, so we had that conversation. We talked about
I was gonna say I was muted for
Okay.
that. Absolutely to other people, even in just the Diginest community, like Avery would have things to say, Molly would have things to say, even Jen. Jen is someone who has dealt with generative AI as a internal teaching tool. She's a master's of social work student. She's had to deal with basically ChatGTP trained to simulate clinical conversation with a client or someone seeking social work, clinical therapy, and also now has experience in terms of. I'll speak very broadly, but the application of tools and technologies, assistive tools and technologies for those with various forms of impairments and disabilities type things. So I'd really like. I don't. The timing for each of those people will be different, but I would definitely, a couple years ago say, oh, the education banner at orthogonal lab or research education lab. I feel like that maybe that will become an increasing. If that's something we revisit multiple times over the course of the summer, whether in this meeting or the other meeting, I mean, I'm certainly okay with that. And last thing about that is there's probably a lot of interesting things from the Princeton Vision Education panel. I was at part of that, and they were a little bit more focused on K through 12, but it's been really interesting to see the changes and then the trajectories, and then I'll just, if we read this later, two seminars of note in the MIT AHA seminar series. One of them I mentioned a while ago was with the folks from Google Learning. That was a very interesting product demo, I will say, and sort of the Google corporate. Here's our pitch about that. And then also the most recent one, which was someone looking at like education and pedagogy and development and kind of scaffolding how to actually get what things lead to actual learning as opposed to just confirmation, or how do people react to different kind of prompts or approaches to getting their views challenged. That one was Christophe Gajos. That was the most recent one, like earlier in May, I think. So maybe those things will come up, and I'd be totally interested in preparing. I don't know if it's going to be an event, but some kind of a structured discussion with all these different points, both from like the Diginets community, the AHA group, Princeton stuff. Like there's a lot of twirly birds in the air. There's a lot of things that have happened that are right there that can be easily assembled into like a nice, I don't know, discussion series type of thing that we've talked about before.
Yeah. So, the final thing I talked about in the meeting was it was a discussion about the open source sustainability project and how, talking about what it is and like the history of it from about 2022 on. So in 2022, we developed the project, and the idea was to simulate open source communities, not just as like an instantiation of project management, but as like a collective behavior problem. And so this is kind of something that we've been building on through our years of funding from Google Summer of Code, from our years of interest and discussions. And so we built out a lot of the tools that we're using today, reinforcement learning components, the large language models, the active inference part, and then having all those, they're kind of, going in different directions. And there's an opportunity for agentive coding to kind of bring that together into a synthesis, but there's also an opportunity to also kind of think beyond what we currently have, and that's always important. So I talked about the higher level or the upper layer of the model and the lower layer of the model. The lower layer is the thing that simulates an agent's ability to do things in a project. And this is, the large language models aspect or the reinforcement learning aspect. Basically, the motivations and behaviors and the skills of the agent. And then there's this higher level, which is the agent-based modeling. And so I talked about all of that. I showed the repository. I went through that. And then I talked about this tool. This is I think a fork of OpenClaw called Claw 3D, where this is a 3D workspace for AI agents. So this is an idea that I had when I was looking at this project, that instead of having an agent-based model, you could also have a three-dimensional model of embodiment for project behavior. So this is where a project is taking place in an open office space where they have agents collaborating, and the idea is that these are you know AI agents that are working in an embodied space. So that's kind of the idea here, but it's interesting because it actually does embody that process of working on an open source project. We don't think about that too much because a lot of open source projects are distributed, and you don't think about an office space per se, but you could embody a project like that in other ways. So it's a very interesting kind of way to develop that upper layer of the open source sustainability project, where a lot of the emergent phenomena happens in open source communities, in open source projects, and being able to diagnose things that go wrong there or understand the collective outcomes of different motivations and things like that are important. Okay. So that was our meeting, open source meeting. Thanks to Jesse for his insights about that. I'd always like to reflect on what we've done in the past week. Okay, so why don't I move on? I did want to talk about this new paper that came out. We have been working on this paper in our cybernetics interest group. We've been working on it for probably 2 years now. So this is a paper that was the genesis of the things that we were doing in the cybernetics interest group. We started that iteration of our meetings in 2023, I think, and we started those meetings by talking about the book on, what was the name of that book, Jesse?
The human use of human beings one?
Yeah, human use of human beings. That was it. And then we went through that chapter by chapter, and then we went through some other papers and more recent papers, and it really helped frame a lot of the work that we'll be talking about in this paper that we just published in a special issue. So the idea here is that we're interested in kind of bringing cybernetics into the modern world. And so what that means is that you're applying cybernetic principles that were developed maybe back 50 to 100 years ago now with things in the modern world. And we use cybernetics today. It kind of is diffused into a lot of areas. But we don't usually go back and revisit some of the core ideas and bring that back. That's what we're doing in our paper. That's what we do in our interest group. So we have this long-standing interest in the Evergood regulator theorem, which was a theorem developed by W.R. Ashby and colleague in about 1970. So it's about a 50-some-year-old theorem. And the idea there is that there's this notion of good regulation, which is that you have a system that has sort of a regulator, and it interacts with the system. It gets feedback from the system. And the regulator is able to sort of auto-regulate or self-regulate itself based on information from the environment based on an internal model with some memory. And in our paper, we also talk about the role of the observer. So there's a regulator, there's a system, and there's an observer that can like correct some of the aspects of that feedback. And so this is an interesting idea that was developed, for just, it was a very abstract idea when it was proposed. It was a highly mathematical idea, but it does bring about this idea of good regulation, or what happens when you have a system with feedback. How does that get regulated so that, say like I can control something very precisely, and not kind of make mistakes. Like, if you're thinking about, like, if you're trying to operate a crane and you're trying to place different things on a surface, or if you're, of course, something as mundane as using your mouse to hit a cursor, or you're using your mouse cursor to hit an icon on your screen. How do you do that effortlessly? And there is this idea that your perceptual system is feedback, using visual feedback, haptic feedback, but you're also using this feed forward information, which is you need to know how to use the system that you're engaged in, so like the technological system. And of course, we talk about feedback all the time, and this is a concept that goes back to cybernetics, but in cybernetics, they didn't really have a good theory of what it meant to be a good regulator. And so that's what W.R. Ashby developed in about 1970. And then that idea persisted through the development of control theory. And so today we think about in terms of control theory and the mathematics of control theory. And so this paper talks about these things, kind of brings together a lot of those threads. The control theory thread, the cybernetics thread, this concept of good regulation, which is like, it's a qualitative concept, but then when you try to apply it, say, to control theory, we kind of have ideas in control theory about how to do good regulation, but then we don't have that larger kind of macro framework for thinking about good regulation, or what it means to be a well-regulated system, or things like that. There is this conceptual gap and this sort of operational gap there that we were kind of exploring with our paper. And then we were, of course, applying this to modern machine learning. So we were actually applying it to the concept of the world model. So a world model is a model that a machine learning algorithm might use to sort of have a context for the world. So if a machine learning algorithm is doing something, or like a large language model is doing something that is, requires a lot of feedback, requires a lot of information from the environment to be correct, it can do that feedback and not, effortlessly, and perhaps not need a human in the loop, or need a human in the loop. That's why we included this idea of the observer. And so that's this concept of building a world model. So this may seem a little weird as to why we cast it this way, but when I get into the special issue, you'll see what I'm getting at. So if you go to our Medium page, this is medium.com URL group. Yeah, I did do a post on this paper when it came out on Thursday. So this paper, we have one iteration of it previously, which was where we put it on the archive, I think last summer. So we've been working on this paper from about, I think we got the request to do, or the invitation to do it in like 2024, early 2024. Yeah. And we did the paper, and we reviewed it in our cybernetics meeting, the draft, and then we put it on the archive. And then, it's been revised in the archive. So it's been living in sort of open access land and archive land for a while. And then, we prepared it for the special issue. So it's there on the archive, but it's also in the special issue as of Thursday. So just so you know, the sort of the vintage of the paper, we've been working on it for a couple of years, and we have like different sort of traces of it in the world. So, but I did prepare a post on this. So this is the post about the special issue. So this is great because now we have our uh, paper in the context of the special issue, which maybe makes more sense as to why we wrote it the way we did. So this is the special issue here, the announcement. Our article in Royal Society A on the Evergood Regulator Theorem as a World Model is out today. Part of the special issue on world models and natural and artificial intelligence. And there's the link. And so our paper, which is called A Good Regulator May Provide a World Model for Intelligent Systems, is now available as part of the Royal Society A special issue, World Models in Natural and Artificial Intelligence. And so they actually prepared an initial article. Every time you have a special issue, there's usually an introductory article that kind of goes over the different articles in the special issue and their contribution to the overall theme. So this theme was world models in natural and artificial intelligence. And so if you go through the article or the special issue, you'll see that there are different articles and they take different perspectives on this same idea of a world model. So this is kind of the part where they talk about our article. So our co-authors here argue that the classic Evergood regulator theorem, or EGRT, of cybernetics can be reconceived as a framework for understanding world modeling in all intelligent systems. The authors propose that effective regulation requires informational correspondences between regulators and the systems they control, such that regulators contain sufficiently complete representations to maintain stability across disturbances, feedback, and changing environmental conditions. So this is basically coming from this idea of the Evergood regulator theorem, that a regulator basically has a model in it of the system. It's not an exact model, but it's pretty close. And that model is refined by interactions with the system so that in ideal cases or under ideal conditions, you get this sort of ergodic mapping or this one-to-one correspondence between the regulator and the system. But oftentimes you can't achieve that. So there is this iterative process of feedback, and you have to build that or refine that representation. And then, of course, you can also use an observer that can supervise that process. And in machine learning terms, that would be like supervised learning, where you're or like a human in the loop, where you're basically guiding that feedback, guiding that world model towards this one-to-one correspondence. So they consider how adaptive mapping and modeling and control can be achieved by self-organizing systems as they couple with the world and generate dynamics that preserve system structure. These concepts are applied to the distinction between purposeful and non-purposeful behavior, suggesting that the illusion of goal-directedness can emerge from feedback processes, with second-order cybernetics providing oversight through internal models that evaluate and refine regulator performance. So second-order cybernetics is basically this model of the observer in the loop. So you have an observer, you have a regulator, and you have a system. And it's interesting that W.R. Ashby didn't really consider the second order cybernetics instance of the Evergood regulator theorem. This is something we introduce in the paper. So this is, kind of getting to this model that we're building, historical model for a world model, and then an approach for the world model, and then we're applying it to different problems or non-traditional computing paradigms that show how this would work in the real world. So we actually introduced a couple of sort of dynamical systems examples for how this would work in a machine learning context. So one was sort of a model of diffusion, where you had in machine learning, diffusion is where you take images and you add noise and you train the model on an image and you add noise to the image and you try to encode that model as a model with noise. And so it's like if I give you a bunch of pictures, you can obviously train a model on those pictures, and you can recover a model that can identify those pictures and put them into different classes. And sometimes it can identify images that it hasn't seen before, but sometimes it can't. Oftentimes it can't. And so the idea of adding noise is that you're adding in variability, and that variety helps the model to generalize. And this is actually something W.R. Ashby argued in his idea of the ever-good regulator theorem, where variety was actually quite important in terms of adding robustness to the model, allowing the model to make that one-to-one correspondence with the system. So it's like if you see a lot of instances of something, or you have a lot of states from which to choose from, that's oftentimes what the real world system has to offer. You can't often say that whatever you kind of come up with as a representation for your model is always going to match the real world, because the real world always has exceptions to it, always has a lot more complexity than what you can come up with. So that's kind of the idea there. And it's interesting because people don't talk about it in that way in machine learning. They usually just talk about like generalization. They talk about like, different types of strategies like data augmentation or other things where you're adding in parameters and things like that. But they don't usually talk about variety as being the key. And so, yeah, and then in diffusion, you have this backward step where you're recovering images from being embedded in noise, and improves, if you add in the forward and backward diffusion steps, it improves the behavior of the model. We considered this in the context of applying the ever-good regulator theorem to forwards and backwards diffusion, as it's defined in machine learning, but also as it's defined in physics as just kind of a diffusion process. Then we also talked about an example of avalanches where you have nonlinear data, and how you can build a model that responds and predicts nonlinear avalanches or nonlinear time series or sequences, which might be useful for large language models. It might be useful for other types of behavioral data, or even like neuroimaging data or something like that. And then our third example was with procedural learning, where you train a model in on one set of parameters, and then you switch to a different model with a different set of parameters, and then you combine those as sort of a generalized learning process. You'll have to go to the paper to see kind of the details of that, the way we work it out. But they're very much like, these examples of how the good regulator would work and interact with data. Okay, so Alicea et al. Show how fundamental connections between world modeling and agency can be traced back to central principles of cybernetics. If regulators are to maintain a system's states within particular bounds, they must in some way be able to encode enough information about those states to model the complexities of the systems they attempt to govern/control. This account also speaks to the potentially broad scope of world modeling and agentic phenomena, and that many of these principles, including apparent goal-directedness, can be identified in the often remarkable adaptivity, one of the hallmarks of intelligence, in quotes, because as you'll see in the special issue, intelligence is we think we know what intelligence is, but oftentimes it's not very well defined at all. And so one of the articles actually talks about intelligence as a question, whether we actually know enough about intelligence to say that something can have a world model. But anyways, so often remarkable adaptivity of seemingly mindless physical processes, such as avalanches and sand piles. However, qualitative differences may be found in systems capable of second-order cybernetics, so governing systems modeling their own governance processes. So again, you not only have the supervised aspect of observers It's not just about supervised learning. It's not just about putting humans in the loop, but it's about this recursive governance of processes. So, like, if you have a process that you're governing sort of at the very fine time scale, like you're giving feedback in, say, the next time step, and you're always doing that, it can often lead to a problem with trying to identify larger scale phenomena. So the avalanche is a very good example of this, where you have a long time series. That time series often it displays these avalanches at a certain frequency that are not predictable, first of all, but also don't just occur based on the previous time steps behavior. It's a cumulative process that's nonlinear. So a lot of times in avalanches, it's where there are a bunch of accumulated events that lead to an avalanche, but there are all sorts of contexts in which an avalanche can occur, all sorts of time scales at which these cumulative events can sit. And so we really need the perspective of a longer term observation to really understand when and where these avalanches will occur. And so this is where we can place an observer in the system to sort of supervise that feedback and say, something didn't happen in the last time step, but it will happen over maybe 1,000 time steps, and integrate that into the model. So that's actually interesting from this perspective of trying to predict things that don't necessarily lead directly from the training data in a machine learning model. This is in line with statements by Hofstadter, as well as Premo Kumar and Krakauer. So these were people who contributed to the volume. So Krakauer, one of our favorites, contributed to the volume. Hofstadter, a famous cognitive scientist that we know of, contributed to the special issue, and other people as well. We'll look at the author list. It's quite interesting. Regarding the importance of strange loops, self-modeling, and self-compression for emergent intelligence. So this is something that where there are all these different concepts for how intelligence kind of works, what's its secret sauce. People have proposed different mechanisms, and we're kind of linking our cybernetic regulator model to some of these larger concepts. The following contribution further explores connections between complexity and world modeling, with formal models potentially fundamental differences between biological intelligences and currently predominant approaches to constructing artificial systems. So yeah, that was our kind of part from our part of this this special issue. So this is the special issue: World Models in Natural and Artificial Intelligence. And this quote that I just read was from the sort of the introductory article here, which we'll go through this table of contents in a second here. So let me go to the special issue. Here it is. So, like I said, all special issues have this introductory article. And this one was World Models, Artificial General Intelligence, and the Hard Problems of Life-Mind Continuity. So this isn't just about AI and world models. This is about sort of this idea of life-mind continuity. This is something that Michael Levin has advocated for, where you have this diversity of minds in different parts of the tree of life. And, you have to think broadly about this, not just in terms of the tree of life, but in terms of machines and in terms of artificial systems, and how that fits into these minds, this concept of the mind. As you know, the concept of the mind is quite fuzzy in a lot of cases, where we have to sort of discern whether something is a mind or something is a brain, or whether those things are separate entities. And this is a central theme in cognitive science that philosophers of cognitive science have struggled with for centuries. So this is definitely kind of try to contribute to this, sort of bolstering this not just the idea of world models, but also this larger theoretical question. So there's this article that actually comes before it in the special issue on the representation complexity of model-based and model-free reinforcement learning. This is Hanlin Zhu, Baihe Huang, and Stuart Russell. Then the main article, which is Adam Safron, Michael Levin, Victoria Clement, Zara, Dalton, Adil. These are people I know from Active Inference Institute. So these are people who are around the Active Inference Institute. They're doing this. They have this perspective of active inference, but also we have people like David Ha, Arena Risch, Melanie Mitchell. These are people who work in machine learning and in that area. We also have
It's quite an interesting group of people. I
yeah
actually didn't really realize until I I've been able to look at anything in depth. So I don't know if we're going to cover any of the other articles next or soon. But
we'll talk about
Melanie
it.
Mitchell is very much the critical of certain things in the AI space. Gershman is Harvard neuroscience guy,
Yeah.
and Josh Tenenbaum is our MIT cognitive science fellow who I mentioned a lot, especially a couple of years ago.
Yeah.
It's a really interesting mix of folks. So I'm curious how the introduction plays out. If it's more, is it very synthetic or is it just sort of presenting different facets?
Well, I mean, they have to go through the articles, and we'll look at it in a minute. So yeah, then finally we have David Krakauer, who's a complexity person at Santa Fe,
Yes.
Sam Gershman, and Josh Tenenbaum, who are like in cognitive science and neuroscience. So we have this very diverse group of people contributing to this article. So this is the introductory article. Again, a very broad sort of take on this. Let's see. This special issue examines how natural and artificial intelligences, as they call AIs, model the world, and what this modeling reveals about cognition and relationships between life and mind. So it's very broad and kind of bringing all these things together. There hasn't been, cognitive science a lot of times tends to sort of dwell, in a sense, on human cognition, because human cognition is like that example we have of, a high degree of intelligence, or like the difference between like animal behavior and human cognition. But actually, of course, there are all these perspectives on animal cognition, and there are all these perspectives on how cognition isn't just something that booped into existence and humans did, but rather is this longer term process of evolution and of things generated by a brain instead of just kind of being a piece of software that you run. And so this is kind of the idea here. Rather than adopting a single definition, this collection considers how world models function and emerge in biological and artificial systems. So, of course, they're also bringing in artificial systems like AI systems, or bioengineered systems in the case of organoids, or things like that. Exploring a diverse range of world modeling, including causal, self-referential, individual goal-directed, collective, and narrative forms. So there is actually this large. It goes well beyond like just thinking about the things adjacent to AI, and kind of really thinking about even things like narrative forms of world modeling, and collective behaviors. A recurring theme is the extent to which current AI systems, trained on vast quantities of data, learn the context-sensitive, temporally embedded, and value-laden dimensions of world modeling. So this is where we have this distinction between merely learning from like just throwing data into a machine, stuffing it in there, and then getting something out that suits our needs, and thinking about the structure of that data instead, and saying, what is it about the data set, or what is it about the training process, before we even think about getting training data. What is it about that training process that can help us to sort of build a world model that's useful? So this is kind of and you're going to see in the special issue, if you read through it, all the different ways in which you could do this. So we want to be able to characterize diverse biological intelligences, or whether their impressive capabilities arise primarily from statistical surface regularities. So, maybe it's just a matter of you take a bunch of data and you stuff it into a machine, and you, figuratively, of course, and if you have the right statistical structure, you can do anything. Maybe that's the way cognition works too. And then, it's definitely in cognitive science, people have made the case that a lot of cognition is about sort of statistical optimization. Like if you think about sensory motor coordination, a lot of that is about things like Fitts law, or can be described in that way, or things that involve very simple feedback loops and just optimizing those. So I mean, there are aspects of that. Or you can think about the free energy principle, even, where you're optimizing for sort of energy expenditure and things like that. So there is this aspect of that thing. But then, of course, maybe it's not that. Maybe you need to think about other types of ways to structure input data, ways to structure experience so that it fits into what's needed. And then I don't know if they deal with this, but there's also this aspect of sort of what different forms of cognition or different intelligences need. So, for example, you may have a very simple intelligence that does the job that requires very little input. Or, you could use like a very simple training set and get a very simple intelligence. That intelligence might not scale, but it does the job. But there are other intelligences if you want to have if you want something that adapts to the real world or work on real-time data or whatever. It doesn't necessarily scale with the amount of data. It just needs a whole different approach or a whole different way of training. And so that's kind of what they're thinking about here. Stitching together a lot of the work of like Levin and other people who have worked on this problem for a long time. The contributions also raise broader issues concerning embodiment, complexity, learning architectures, and the social and scientific contexts in which world models operate. With this collection, we hope to clarify the conceptual landscape, identify key points of similarity and divergence between natural and artificial minds, and outline questions that may guide future research on the forms of world modeling that support grounded understanding, robust agency, potentially human-like general intelligence. This special issue invited contributions focusing on the following questions. So there are 4 questions basically that were in the call for papers. The first is, what range of world models might we associate with which systems, and what are their functional properties with respect to inference and learning? The second one was, which kinds of world models might be associated with which conscious phenomena? So thinking about consciousness or about different types of things in cognition that we'd like to emulate. Which kinds of world models might be associated with large language models, and to what extent this might change with further technological developments. And then which kinds of world models are characteristic of all life, ranging from animals to plants and fungi, or even individual cells. So in posing these questions, we can basically say that world models have multiple meanings, each of which could be differently valuable for different contexts. However, such a broad range of connotations run the risk of becoming semantically vacuous or even misleading, perhaps akin to the way in which consciousness has become something of a suitcase word in cognitive science, and potentially a place for hiding our ignorance with respect to phenomena that challenge our understanding. So, again, we don't want a situation where world model is kind of thrown around as a term of art without the actual art behind it. We want to have, and sometimes it's about like, this is what I mean by world model, or this is my world model, and it might be a world model for very small data sets. It might be a world model for very large types of biological data. It probably is not going to be a one size fits all thing. Yet, what if world models and consciousness had similar ambiguities, partially due to there being deep connections between these concepts? And that world modeling could potentially help explain how some physical systems have subjective experiences. That could be as well. Um, and then this gets into sort of the different types of different papers in the volume. So this is a quote from Douglas Hofstadter, who wrote one of the papers in the collection. And in his paper, he wrote, "There's no magical extra thing going on inside our organic human brains that makes their eyes realer than potential eyes of future computational systems." So when he talks about eyes, this goes back to some of the work that he's done on cognition and the strange loop stuff that he's done and all that. So eyes, I think, stands for intelligence. And so, this is just kind of like saying that there is no real difference or anything magical, the difference between our brains or our minds and the minds of a computational system. It's just the presence of a complex and abstract pattern that I call a strange loop that is needed. So this is the strange loop reference. So when it comes about, and I fearfully suspect that it will come fairly soon, perhaps even by 2033, the real miracle will not be the leap of consciousness substrate from carbon to silicon. The greatest miracle was when inanimate matter gave rise to animate beings. Compared to that astonishing volcanic explosion a few billion years ago, the looming takeover of meaning, concepts, ideas, beliefs, thinking, sentience, and consciousness by computational entities from biological entities is just a minor blip in the steady march of evolution on the surface of planet Earth. And thus, perhaps sooner than you think, your royal I-ness will be looking up to an even more exalted I-ness. That's a day to greatly fear, so at least say I. He's very poetic in his writing, so, basically this means that you have different intelligences that aren't really that different. It's just kind of, um, just thinking about the different sort of, uh, maybe thinking about this from an evolutionary perspective and thinking about the different types of um, intelligences or consciousnesses that already exist. So that's what he's getting at here.
In the Daniel Fagella worthy successor camp of things, who very much appreciated the article series and praised Adam Safron on this, I think he would appreciate Hofstadter's comments in the sense of, oh yes, of course, there's a very particular natural trajectory of development that will supersede what is currently human. So there are things coming and beyond us in that sense. So it's really interesting to see how that's going to play out with like different camps and then approaches in perhaps in the article series.
Yeah. So if we go back to the special issue, of course, we have the introductory article, and then we have Douglas Hofstadter's article, "Is There an I in AI?" And so this is the one that I just talked about. That's where his little passage came from. And this is basically, here in a nutshell is a thesis of the essay. When words act like things in the world, then they refer to those things. Then they mean those things. If and when that happens, then thinking is taking place behind the scenes of those words. And when there is thinking, there is consciousness and a genuine full-fledged I. So that's basically the idea that he has. So it's about kind of this, thinking about language, thinking about how they're embodied in meaning, and then the thinking kind of results from action. And that's very consistent with what we think about in cognitive science. And so this is, of course, not just true of humans or of animals, even this is true of large language models. And so, thinking about the different behaviors, so the words thrown
Like the
about
bit,
by,
I think, therefore I am.
yeah, I guess
Is
so.
that
That's a good way to put it. The words thrown around about by today's large language models mean something, exactly to the extent that their behavior matches with or meshes with the world's behavior. So, this is a provocative example involving GPT-4. The response of GPT-4 to a prompt asking her to explain how to make a stable pile out of a book, a laptop computer, 9 eggs, a bottle, and a nail, is kind of the idea. And then you have to kind of come up, the model has to come up with that response. And then it's basically, that is kind of here's your intelligence, I guess, a full fledged intelligence. Um, where does the solution come from if not from understanding? And he talks about that this is stuff that people were thinking about 50 years ago. Terry Winograd's Shirtley program um, is, there's no real difference from that form, that iteration of artificial minds, but it's very much greater. And so there's a greater understanding to be had from GPT-4, and that's what kind of makes it sort of, you know, kind of mind-like, or at least people marvel at the mind-likeness of that model. So that's the first article. The second article, Large Language Models and Emergence. This is from David Krakauer, Melanie Mitchell, and John Krakauer. This is, again, just kind of thinking about large language models from a complex systems perspective, thinking about emergence as a component of this. So they talk about the more is different article, which is a classic article in complexity theory that talks about it sort of staked out the terms of emergent complexity and how that is a way we can think about interacting parts, producing something that is sort of at a level greater than the sort of the atomistic level of the components that are interacting. And so they talk about emergence as being this more is different idea. Um, and then then we also have to think about intelligence, which is a consummate emergent property manifesting increasingly efficient uses of emergent capabilities to solve problems. This is captured by the idea less is more, which is actually a little bit different. In this paper, we examine claims that large language models exhibit emergent capabilities, and then secondly, ask whether large language models possess emergent intelligence. And so it kind of captures both of these ideas and brings them together. I think that'll be a good paper for people who want to know more about sort of, when people say that uh, a solution that an agent is making is emergent, it's kind of emerging from different parts of the training data, that they be more precise about what they mean by emergence. In general, the concept of emergence has really suffered from a lack of precision throughout its history of use. So people will say something is emergent, and it's like, well, can you quantify the emergent properties of this system? And it's hard to do because, of course, it's based in interactions, but it's also somewhat subjective. You see something that isn't in the sort of the state of the parts of the system, and you say it's emergent, but you don't know whether that's a process that's constructed something new or if it's just a product of things that are interacting and has no real descriptive value. And to understand that, you'd have to go back into the philosophy of emergence. But basically, there is this confusion as to whether something is emergent or not.
I'm curious to look at that in the context of we've talked about Krakauer a fair amount in different David Krakauer from Santa Fe recently,
Yeah.
and probably the last few years. But I'm curious of this version of his treatment of complexity and emergence. I really still like the Sean Carroll, I think it's Sean Carroll, Mindscapes podcast,
Yeah.
where he's because he gets at that. He at towards I think the last quarter of it, he kind of that's when emergence kind of comes up and he gets it. I think his take is, if I'm doing this, if I'm remembering him correctly, he was very much trying to rein in the scope of like emergence as a term. And I don't think he was dismissive is way too strong a word, but very aware of the problem. I think that Bradley just presented. So I'm curious how it comes off here in the context of this article series. So it was him, Mitchell, and his brother, the other Krakauer.
Yeah.
I look forward to reading that, and that might be something to kind of, I don't know. This whole issue is sort of extremely great fodder for, as we talked about recently, picking things up again, but also just like straight up cognition futures, and we'll see if I get into the diverse Disney, the summer school, but just like there's sort of this powder keg of, okay, we have all these opinions here presented in this article that's sort of custom made by Adam and Mike Levin, and I don't know. We'll see where it goes. I'm curious. We can go through as much as you want, but I'm curious. One of my questions, I may have to step out before 12 o'clock ends. I don't quite know yet.
Okay.
But I'm gonna want to slip this question in for them to think about it. Sort of like, what do you want to do next? And I don't. We can go back to the articles, but like, do you have any like particular follow-up you want to do? Or I'm also in the back of my mind, I'm doing some of the website updates and things, and like, oh yeah, like the reimagining cybernetic projects, cybernetic interest groups, whatever we're calling it. But like, is there anything any particular directions you want to go with? Not just our article, but like kind of this topic that's on your mind.
So I think there are a couple things that I can think off the top of my head that would be worth pursuing. The first, of course, is the sort of the core model that was proposed in the paper here. I mean, you have a certain amount of space you can use, and you have to introduce things and motivate them and put them into the context of what we want for the special issue, right? So we had to talk about certain things there. But I think there's a more general kind of development of the model is taking the model maybe and applying it to very specific problems, or seeing like, maybe there's a cybernetics theoretical question, which is what is, when we talk about good regulation, and we defined, I think we did do a good job of defining it, sort of putting the nails in the board to keep it kind of from floating off into space. But it's still, what do you mean by good regulation? Are there things that you can add or subtract from the model that would kind of deviate from that? And a lot of that has to do with kind of its relationship to control theory, which is not, something I'm an expert in, but definitely has some ties back to things like reinforcement learning and active inference. And so that's something we didn't get to explore too much in the paper, but is interesting from a sort of a perspective, especially like active inference, because we've been doing a lot of interaction with the Active Inference Institute. And I think it'd be interesting to see kind of that modern treatment of the good regulator. And so that's one thing. Another thing is to say, maybe talk more about like, maybe get another concept from cybernetics and look at that in relation to the Evergood regulator theorem. So now that we have the Evergood regulator theorem sort of explored enough to kind of bring that into the modern world or consider it in the modern context, what other concepts can we do that with? So I don't remember, and there are a lot of concepts from the cybernetics literature that are really interesting, but that kind of live in this space of like 50 years ago. So
right, like, yeah.
So anyways, yeah, and we could do something like that, or applying this to sort of more directly to an applied setting of like machine learning. or you think about like actual algorithms, improving upon algorithms and things like that, or even like for agents, like if we plugged the Evergood regulator into a Brainberg vehicle, what would that look like? Because Brainberg vehicles are this sort of very simple first order feedback, and that's like good for like reproducing maybe certain behaviors, like taxis, like chemotaxis or phototaxis. But what happens if we like build a model of good regulation that's a little bit more detailed? We have an observer, things like that. What can we do with a Brainberg vehicle? I don't know.
Yeah, and like I apologies sort of bringing that up in a maybe unprepared fashion, but it's just something that I'm thinking about a little bit. I don't have any concrete leads beyond what any, well, not even concrete, but many leads beyond what you said. But I feel like there's definitely, I kind of hope that Amanda gets to. I don't know if she's read the published version in the context of the other articles yet or not, but I'm hoping to reconnect with her soon, and she's at different time zones now, so maybe that discussion, if we can get her or all of us together, sort of a Condition Futures reading group type, or cybernetics reading group, kind of both the same or whatever. Some kind of a informal meeting of us together, I think, would churn out some interesting things to that end. But yeah, I feel like there's both to like champion cybernetics theory and reimagining cybernetics, whatever sense, yes, but also just seeing some of the ways. I think going through the articles in the issue might be quite fruitful on many related fronts. So I think that's what I'm going to try to do next, in maybe a week or two when I have the actual time to read that material. But yeah, I don't know. It's just I feel I'm tantalized by all this like cool stuff and the different authors' perspectives, and like, okay, great, and maybe because I'm always striving for some of the synthetic work, and maybe doing some kind of a review on the special issue itself, and will be a step forward too. But that's it. I don't have any. It wasn't a question that I already knew the answer to.
Yeah.
So we'll see where that goes.
Okay. Well, we'll continue on with the special issue here. That was this article. Then there's levels of analysis for large language models. That's Thomas Griffiths, Alexander Koo, and some other people. This is, of course, it has to do with Mars levels of analysis. And of course, if you remember that, it's where you have these different levels of sort of cognitive analysis. So, it goes from sort of a hypothetical space to an implementation space, basically. And so this paper kind of frames language models or large language models into that framework. So it's kind of thinking about studying, interrogating the cognitive aspects of these models from Mars framework. So modern artificial intelligence systems, such as large language models, are increasingly powerful, but also increasingly hard to understand. Recognizing this problem is analogous to historical difficulties in understanding the human mind. We argue that methods developed in cognitive science can be useful for understanding large language models. We propose a framework for applying these methods based on the levels of analysis that David Marr proposed for studying information processing systems. By revisiting cognitive science techniques relevant to each level and illustrating their potential to yield insights into the behavior and internal organization of large language models, we aim to provide a toolkit for making sense of these new kinds of minds. So they throw down the gauntlet, and they give this example from David Marr's 3 levels. So the first level of analysis is computational, and that is what problem is being solved and what is the ideal solution. And there's this distinction between cognitive science and artificial intelligence. So in terms of cognitive science, this computational level is understanding behavior in terms of optimal solutions to environmental pressures. So the computational level of analysis, an example would be Bayesian models of cognition. In artificial intelligence, because cognitive science is about bridging that gap in part between AI and human systems or cognitive systems more generally, you have, it's kind of, when Marr was thinking about his levels of analysis, he was also thinking about artificial intelligence. At that time, it was connectionism, but still you had this analogy. So in artificial intelligence, the computational level of analysis is understanding behavior in terms of the training objective. So this is where instead of thinking about optimal solutions to environmental pressures, you're thinking about the training objective. So this is something like next token prediction, but also understanding behavior in terms of deviations from optimal benchmarks. So an example of that would be violations of probability axioms. So basically, the computational level in cognitive science, it's a Bayesian model that is, has a prior distribution, and then you sort of correct your output based on correcting or refining those priors to match the environment. In AI, we're doing things like next token prediction, which is very proximal, and then these violations of probability axioms, which deal with out of distribution data. We made a similar argument in our paper about different, when we were thinking about avalanches and the role of the observer. So the observer deals with these larger global issues. The regulator deals with these proximal issues. The next level of analysis is algorithmic. So that's how is the solution approximated and what representations and processes are involved. So this is in cognitive science, it's inferring mental representation and processes. They're behavioral experiments. So these could be things like reaction times, error patterns, or similarity judgments. And then thinking about an algorithm of behavior, basically. And then in artificial intelligence, algorithmic level of analysis is inferring representations and processes via behavioral analysis. So this is analyzing systematic errors, soliciting similarity judgments, uncovering hidden associations. So it's really thinking about that algorithm at the core of the cognitive process. And then implementation level of analysis, which is how are the representations and processes physically realized. So this is where, you're of course dealing with neural circuits in cognition, in animal cognition. You're dealing with population activity of neurons, and you can measure those with single unit recordings, fMRI, or MVPA. It's basically verifying the behavior with some, mechanism. And so in cognition, we often have neural circuits. So the cognition behaves on these neural circuits. We don't really understand how it works, but we can infer certain things about that process. And it's, in cognition, we often use the analogy that it's software running on hardware, but really it's probably not that. It's probably more involved. So, we need to look at that implementation on hardware, mind the analogy, to really understand the behavior and how it's generated. So in artificial intelligence, we have a similar thing where we study artificial neurons, circuits, and population activity using techniques like activation patching, sparse autoencoders, and representational geometry analysis. Basically looking at things like a neural network or a connectionist network, and then looking at, we can trace back to the pattern of activation within those networks. So we talked about methods last week that people use at Anthropic to do that. And there are other types of methods like credit assignment that are important. So you know kind of basically what the pattern of activation is for a certain concept. And you can trace that back. And so it makes the artificial intelligence system more interpretable, and it allows you to really understand how the activations are being generated. So you know maybe if something is spurious or not. So that was a good kind of a way to address, at least in terms of cognitive science, being a rigorous cognitive scientist, addressing this idea of intelligent behavior. Okay. And then this next paper is Goals and the Structure of Experience. This is a paper that I remember as a preprint. We cited this in another paper. This is Stas Tiomkin, Angela Langton, and Nadav Amir. And this is on sort of this idea of sort of purposeful behavior and goals, and how this, how we can think about this. So purposeful behavior is a hallmark of natural and artificial intelligence. So we know that there is this concept of purpose in cybernetics as well. If we go back to the paper on the 1943 paper that we talked about in our reading group, and
behavior, purpose, and teleology.
Yes, behavior, purpose, and teleology. People have been thinking about this in cybernetics, but also in cognition. So the acquisition of purposeful behavior is often believed to rely on world models comprising both descriptive what is and prescriptive what is desirable aspects that identify and evaluate states of affairs in the world, respectively. Canonical computation accounts for purposeful behavior, such as reinforcement learning, posit distinct components of a world model comprising a state representation and a reward function. So you often have in things like reinforcement learning a descriptive aspect, which is the state representation, and a reward function, which is a prescriptive aspect of behavior. So basically, when you're looking at purpose, you think about that a system does something, it tries to achieve something with a prescriptive thing that it's trying to achieve it with. So, you have these rewards for different behaviors or different states. The highest reward is selected, and then that behavior is implemented. And then you know that, like, if the reward is consistently high, that state will be consistently represented. That's basically the idea of purposeful behavior, that it's this function of reward, but also this output that you can measure. However, an alternative possibility, which has not yet been computationally formalized, is that these two aspects instead co-emerge interdependently from an agent's goal. So oftentimes in reinforcement learning, we think of rewards being sort of the precursor to state representations, but we don't, maybe that's not the case, because rewards are continually updated. And it is this loop of where you have rewards, you have states, the rewards get updated, the states get updated, and one has to result from the other. We can think of the causality, if at a very superficial level, we think the causality is basically a reward will determine what states are represented in the behavior. But if we think about the whole system as this set of feedback loops, or this, this sort of circular causality, then it's a little bit different, because then we can't really identify where the rewards change and where the state representation changes and so forth. So these things have to co-emerge in some way, and they co-emerge from an agent's goal. So we can actually look at the goal as the causal agent that changes both of these. Here we describe a computational framework of goal-directed state representation and cognitive agents, in which the descriptive and prescriptive aspects of a world model co-emerge from agent-environment interaction sequences or experiences. And so here they're drawing from Buddhist epistemology, where they introduce a construct of goal-directed or telic states defined as classes of goal-equivalent experience distributions. Helix states provide a parsimonious account of goal-directed learning in terms of the statistical divergence between behavioral policies and desirable experience features. Okay, so that's, we cited that in the paper that we did on cybernetic imperatives. So this was the preprint version. So a lot of these papers have lived as preprints before they were in the special issue. So that was that paper. The next paper is what does it mean to have an experience? Two kinds of narrative world models. This is an individual contribution, and this talks about sort of the narrative world model, which organizes actions and events into temporal episodes with defined beginnings and endings, linking these endings to emotional outcomes. And so this is kind of thinking about, the role of narrative and the structure of narrative in building these world models. And this is important, of course, for large language models because they deal with narratives, they build narratives. Then there's human level learning of complex novel tasks, is theory-based modeling, exploration and planning. This is a paper by a number of authors, including Josh Tenenbaum and Sam Gershman. This next article is Empowerment Gain in Causal Model Construction. Children and adults are sensitive to controllability and variability in their causal interventions. This is a developmental perspective. This is Alison Gopnik is on this paper, along with some of the co-authors here. And so this is about, Alison Gopnik does this work with development and thinking about development as applied to artificial intelligence. So in this paper, the abstract talks about learning about the causal structure of the world is a fundamental problem for human cognition. So learning about the causal structure and development, learning what comes first, what comes next. And learning that from interacting with the world. So if you're a baby, you interact with the world, you figure out how things work through causal structure, and you kind of experiment with things, and that's how you develop this sort of intuition about causality. Causal models, and especially causal learning, have proved to be difficult for large pre-trained models using standard techniques of deep learning. So we know kind of that this happens in the development of animals, of humans, but we can't necessarily replicate this in artificial systems. In contrast, cognitive scientists have applied advances in our formal understanding of causation in computer science, particularly within the causal Bayes-Net formalism. So they're using Bayesian formalisms for this, to understand human causal learning. In the very different tradition of reinforcement learning, or RL, researchers have described an intrinsic reward signal called empowerment, which maximizes mutual information between actions and their outcomes. So this is comparing kind of the standard approach of causal Bayes nets with this idea of empowerment in reinforcement learning. Empowerment may be an important bridge between classical Bayesian causal learning and reinforcement learning, and may help to characterize causal learning in humans and enable it in machines. So we can actually use this concept of empowerment to think about, or this is an intrinsic reward signal, to think about, the way this works in animals, and then think about how to apply it to machines. And if an agent learns an accurate causal world model, they will necessarily increase their empowerment, and increasing empowerment will lead to a more accurate causal world model. So it's this sort of circular causality in the sense that you have this conceptual thing, this feature that you're building into the model, and you basically use it to acquire this world model that will increase the empowerment of the model, which increases its ability to understand causality. So they bootstrap each other. Empowerment may also explain distinctive features of children's causal learning, as well as provide a more tractable computational account of how that learning is possible. In an empirical study, we systematically test how children and adults use cues to empowerment to infer causal relations and design effective causal interventions. So they actually brought from some studies here from children, from human children, to show how this works. Okay, this next article, a sentence is worth 1,000 pictures. Can large language models understand human language and world behind words? So this is using lead speak, I guess. And there may be a reason for this. This is Gary Marcus as an author on this, by the way. So the abstract reads, the current generation of large language models has been linked to claims about human-like linguistic performance, and their applications are hailed both as a step towards artificial general intelligence and as a major advance in understanding the cognitive and even neural bases of human language. To assess these claims, first, we analyze the contribution of large language models as theoretically informative representations of a target cognitive system versus atheoretical mechanistic tools. Second, we evaluate the model's ability to see the bigger picture through top-down feedback from higher levels of processing, which requires grounding in previous expectations and past world experience. We hypothesize that since models lack grounded cognition, they cannot take advantage of these features and instead solely relies on fixed associations between represented words and word vectors. So they actually use, in the assessment, they use a novel LEET task, which explains the LEET speak in the title, which requires decoding sentences in which letters are systematically replaced by numbers. So LEET speak is where you're replacing letters with numbers. So in human, the A is a 4. In language, the A's are 4s. And then the world and words, those words both have zeros instead of O's. So you're just, it's a cipher basically. And so the model has to learn that pattern and then decode that. In line with our hypotheses, the results suggest that humans excel at this task, whereas models struggle. We interpret these results by identifying the key abilities that are still missing from the current state of development of these models, which require solutions that go beyond increased system scaling. So that's kind of their take on this. It's an interesting kind of study. So some of these are, kind of ideas-driven, theoretical. Some of these are studies. Okay, then there's unexpected benefits of self-modeling in neural systems. This is actually Michael Graziano is on this paper with some co-authors. So he does a lot of things in thinking about consciousness and other types of cognitive science issues. So this is thinking about self-models and self-modeling in cognition, and that's sort of the basis for his work on consciousness. So, thinking about modeling the self in the mind. So how do you apply that to, different types of artificial systems? So self-models have been a topic of interest for decades in human cognition and more recently in machine learning. Yet what benefits do self-models confer? Here we show that when an artificial network learns to predict its internal states as an auxiliary task, the network becomes simpler, more regularized, and more parameter efficient. So this is where, you want to be able to predict internal states. So this is something that oftentimes artificial networks don't do. They don't have internal states. They don't have a model of the self. And so being able to do that, it makes for a more efficient network just simply because it's reflecting on its own inputs. It's reflecting on its processing. And this is very similar to the types of things we see in interoception, where you have sensory abilities in animals where it can detect the state of the body, the state of the self, and that can feed into cognition that way. To test these hypotheses of self-regularizing through self-modeling, we used a range of network architectures, performing 3 classification tasks across 2 modalities. So in all cases, adding self-modeling caused a significant reduction in network complexity. The reduction was observed in 2 ways. So the first way is the distribution of weights was narrower when self-modeling was present. Second, a measure of network complexity, the real log canonical threshold, or RLCT, was smaller when self-modeling was present. So complexity decreased, the distribution of weights became narrower, and the predictability, I guess, becomes higher, and the precision becomes higher. These results support the hypothesis that self-modeling has a restructuring effect, reducing complexity and increasing parameter efficiency. This self-regularization may help explain some of the benefits of self-models reported in recent machine learning literature findings, as well as the adaptive value of self-models to biological systems. In particular, these findings may shed light on the possible interaction between the ability to model oneself and the ability to be more easily modeled by others in a social or cooperative context. This is, of course, feeds in this idea of the body schema, which is the brain's model of the physical body, and having a body schema for an agent. Now, an agent, of course, if it's not embodied, what is the body schema? Well, it could be something just having to do more generally with an internal state. So this is where you're just monitoring performance and then putting it in the context of current performance. So it's an interesting concept. How to apply it to a model? Well, that's kind of, maybe it's a test of embodiment, in fact. Maybe we do need embodiment for something like this. But again, these papers raise a lot of questions, and that's what this is for. It's for kind of driving future work. This is, of course, our article, which I won't go through because we're already familiar with it. This is a paper by Dalton, Michael Levin, and Francesco Sacco, Topological Constraints on Self-Organization in Locally Interacting Systems. And this is kind of getting at this idea of emergence and self-organization, and thinking about how there's a topology there. So all intelligence is collective intelligence in the sense that it is made of parts and must align with respect to systems level goals. To that end, consider a system on the vertices of a planar graph with pairwise interactions prescribed by the edges of the graph. Such systems can exhibit long-range order, distinguishing one phase of macroscopic behavior from another. In a network of interacting systems, we may view spontaneous ordering as a form of self-organization, modeling neural and basal forms of cognition. Here we discuss necessary conditions, the topology of the graph for an ordered phase to exist, with an eye towards finding constraints on the ability of the system with local interactions to maintain an ordered target state. So this is actually introducing this idea of free energy and the free energy principle. So thinking about these kinds of models of networks and thinking about long-range order and how those things kind of come together. This is very physics-like. They consider 3 different types of model systems. The POTS model, which is this cellular POTS model, which is used in CompuCell 3D, but it's a physics model that deals with these lattices and coordination across lattices. They also consider autoregressive models, which are very important in different sequences in machine learning models. So we often use autoregression, large language models, and we use autoregression, of course, in our avalanche models as well. So it's very important to sequential data and things like that. And then hierarchical networks, where you have structure that's hierarchical, that you have things underneath other things. And again, those are all kind of these, can serve as these sort of distributed systems with long-range order. So from these 3 model systems, we show how the combinatorics of interactions on a graph prevent or allow spontaneous ordering. As an application, we are able to analyze why multi-scale systems, like those prevalent in biology, are capable of organizing into complex patterns, whereas rudimentary language models are challenged by long sequences of outputs. So it's basically trying to build upon the sequential nature of language and the sequential nature of data to improve in thinking about like how this is dealt with in physics and how this is dealt with in cognition to bring that into artificial intelligence models. So it's an interesting kind of approach there. There's another paper by George Northoff, Samir Abbasi, and Yasser et.al. What physics offers for artificial intelligence, lessons from the brain's inner time and its dynamics. And this sounds like it's sort of a neuroscience paper. So this is actually thinking about dynamical neuroscience and the different scales of activity in the brain over time, and thinking about synchronization and how that all can be applied to different types of AI models. It's really interesting. They approach this from the perspective of the brain's intrinsic neural dynamics, of spontaneous activity. So, this is the structure of a lot of experience. So, in particular, we focus on the brain's intrinsic neural dynamics of spontaneous activity and how it uses them for dynamic input processing and encoding in order to participate in the world's physical time. And so what they mean by participate in this context is that behavior becomes part of the input dynamics. So again, it's that loop where you have things that are happening now that go back and become part of the input for the next time step. And so there's this circular causality that's inherent in this sort of participation. And so when you think about things like listening and dancing to music or other types of behaviors where it's dependent on interacting with a stimulus, these are all things that are very much in this vein. So, if you think about an artificial intelligence model, if you just train a model and then separate the training from the testing, you don't have this problem. But when you integrate the training and testing, in other words, when you have to train the model in real time as it's behaving and trying to predict things, especially when you don't have sort of a baseline training, then this is where this comes into play. And this can build up a world model from experience. And they use this analogy of sort of dynamical neuroscience to sort of draw from for this. Okay, so that's sort of the physical perspective and how to think about that. And then this another article by Michael Levin with Nicholas Rouleau, which is Brains and Where Else, Mapping Theories of Consciousness to Unconventional Embodiments. And so this is where thinking about theories of consciousness and how this is associated with brains. So it is assumed that a useful theory of consciousness will explain why consciousness is associated with brains. However, the findings of evolutionary biology, developmental bioelectricity, and synthetic bioengineering reveal ancient pre-neural roots of many mechanisms and algorithms occurring in brains. So this is again this idea of diverse intelligences. Minds may have preceded brains. And you can get, into this literature, and there are these different constructs people have used to hypothesize what minds look like in physics. There are things like Boltzmann brains and things like that. Anyways, this is kind of grounding this a little bit more rigorously. So most work in the emerging field of diverse intelligences emphasizes externally observable problem-solving competencies in unconventional media, such as cells, tissues, and life technology chimeras. So these are just organisms that are made from two different organisms, or systems made from two different organisms, where you can combine different types of capabilities into a single test bed. Here we inquire about the implications of these developments on theories of mind. Specifically, we analyze popular current theories of mind to ask what features of each theory specifically pick out brains as a privileged substrate for inner perspective, or do features emphasized by the theory occur elsewhere? So, do you need a brain for a mind, or can you run a mind somewhere else? And this ties back to a lot of Levin's ideas about cellular minds and things like that. And of course, there are single cell organisms that don't have a brain that do things that are very cognitive. And there are a lot of papers on this where they explore things in different model organisms, single cell organisms that are, very cognitive, and you can interpret their behavior as cognitive. And so you can have different substrates that you would find, say, in single cells that are very similar to brains. So you could have like a substrate of biochemical reactions, and it would do very similar things to brains. So that's what they're getting at with this, that you can basically, if you use that hardware-software analogy again, the hardware could be anything that is complex, and the software is still the mind, that you might have a set of biochemical reaction networks that do things that are mind-like, not because the biochemical network is similar to brains, but because it just provides a substrate for computation. And one of the things you might think of is like, why is so the mind is this thing that floats around evolution and kind of affixes itself to different systems? No, it's just simply that the mind in this case is a set of imperatives, or a set of things that or a single cell organism or an organism with a very complex brain needs to do, and it just uses the substrate that's available to it. I mean, it still doesn't describe, or it still doesn't predict why we might have large brains or complex brains or simple brains or whatever, but it is a thing worth asking as to whether you need brains to have intelligent behavior, to have minds. And so this, of course, is relevant to artificial systems. We don't need to mimic the brain when we build an artificial intelligence, if this is the case. But it also describes maybe other modes of intelligence where in lineages of the tree of life where you don't have brains, like single cell organisms, or even in slime molds, which we see collective behaviors that are mind-like. Okay, so again, they ask this question about the theory of mind, that it could occur outside of brains in that context. We find that operations and functional principles of most theories of mind are not confined to neural substrates, and that the focus on brains is more driven by convention than by specific context of existing theories of consciousness. Encouragingly, several contemporary theorists have made an explicit effort to apply their theories to synthetic systems in light of recent technological developments in artificial intelligence and organoid bioengineering. So they have the organoid reference in here. We talked about organoid intelligence and how that substrate is actually, I guess, quasi-neural, because you may have brain organoids that do things that are intelligent, or you may even have just regular organoids that are clusters of cells in association that form the system, and they may actually do things that are mind-like. So in organoid intelligence, of course, we have that simple sensory motor feedback loop that we can use to play Pong. That's a brain organoid, but it's not exactly the same substrate that we generate that behavior with, say, in humans. And so that suggests that it's substrate independent. So we suggest that the science of consciousness should remain open to minds and unconventional embodiments. It's a lesson from that paper. Okay, and then there's another paper by Michael Levin with Benjamin Lyons, who Jesse mentioned. And this is Cognitive Glues or Shared Models of Relative Scarcities, the Economics of Collective Intelligence. This has to do with this concept of cognitive glue, and just thinking about the technological approaches to mind everywhere idea, or TAME, which Levin introduced in another paper. So thinking about an economy as a complex system consisting of autonomous elements at multiple scales, which exhibit adaptive problem-solving capabilities, is a way to think about complex systems, and thinking about maybe how a distributed emergent system can solve problems like a mind. So they're thinking about an economy in a society where people are exchanging things, and the economy has its own sort of self-regulation capabilities and things like that. So, what keeps that system running? And that's the idea of a cognitive glue. So if you think about like a distributed system, like an economy as a mind, then what's the cognitive glue that keeps that going? And so it turns out that it's not the agents necessarily, it's the price system, which is the cognitive glue of the economy by acting as a coordinating affordance that enables members to form plans that are mutually compatible. So this is the thing that sort of enables this emergent phenomena in the economy, the self-regulating emergence, and this is the price system. So using the collective intelligence framework of TAME, we elaborate on various aspects of the economy that make it useful to model the economy as a collective intelligence. We argue that any cognitive glue must solve the same kinds of problems that the price system solves, and broadly the same way that the price system solves it. And thus the price system serves as a generic template or abstract model for all cognitive glues. Finally, we describe some research ideas that combine concepts from biology and economics in hopes of inspiring interdisciplinary collaboration. So we're dealing here with these self-organizing emergent systems that have agents that are interacting. And those interactions form this higher level order. Now there's, of course, something holding this all together, which is the price system that's enabling the interactions between people, enabling efficient interactions between people. And that is this idea of the cognitive glue, and that coordinates everything and makes sure that this thing operates in an intelligent manner. So, you don't have people chasing prices that are suboptimal. Usually have people chasing the cheapest price, or maybe charging the most for things when they can, and things like that, and knowing those things across the market. So this is an interesting idea, and you can apply this more broadly than the economy. It's just the system they used, but it's definitely, and I think if we think back to our open source communities, what's the cognitive glue of an open source community? I don't know. It could be like integrity. It could be trust. It could be sort of a value in the project. It could be like maybe maintenance of the project. There are a lot of things that could be the cognitive glue there. But it's worth thinking about they classify as mathematical finance and systems theory. So thinking about this in terms of an artificial system, you might have this might be something where if you have teams of agents where this becomes very important. Okay, then there are two other papers. There's Revisiting Rogers' Paradox in the Context of Human AI Interaction, and then Artificial Intelligence for Science, the Easy and Hard Problems. I'll talk about the last one here. This is the Sam Gershman Rotary Battle Day paper. And this is where they're thinking about how to apply AI to science. So the abstract reads, a suite of impressive scientific discoveries have been driven by recent advances in artificial intelligence. These almost all result from training flexible algorithms to solve difficult optimization problems, specified in advance by teams of domain scientists and engineers with access to large amounts of data. Okay, so these seem like, we know kind of what, we're kind of waiting for the method to solve these problems with. But again, this is the kind of thing that is, these are easy problems. These are things that we know we can solve with artificial intelligence. So if we think back to some of the work that's been done on protein folding and simulating proteins, protein dynamics. That was originally done by teams of scientists using like physics engines and things like that, and they were able to achieve a lot. And then AI came along and helped do that work faster. So it wasn't that it enabled a new mode of discovery, but it just basically built upon the previous work that was done, just doing it faster and more efficiently. So we had the domain experts, we had we actually had the algorithms. We just needed to make them go faster and have a sort of something that would help us enable some of the things we couldn't do with, we had limitations of computational power. We had other things, problems that got solved through artificial intelligence. So the easy problems are extremely useful for sort of identifying the utility of using AI for solving scientific problems. But these kinds of problems are really easy in the sense that they're already well worked out and that we know kind of the parameters for which the solution resides. So we're just looking for the solution. On the other hand, the other part of scientific research is coming up with the problem itself, or the hard problem. And this is the thing that we can't really do with current algorithms. So when we talk about things like an AI scientist, the AI scientist, is trying to do the latter. So it's like where we feed a bunch of data into the algorithm or into an AI model, and we expect to get out of it some sort of insight, some sort of problem that's novel that can solve something in the real world. So this is the hard problem. This is actually what a lot of scientific research actually is, setting up the problem to be solved. So at one time, protein folding was this kind of hard problem where we didn't know why proteins folded and we had to figure that out. We had many years to do that, and then once we figured that out, then we applied our AI model. In this case, what we're saying in the AI scientist case is we might approach a novel issue by maybe going through a bunch of data, training a model, and then identifying these questions, and then furthermore identifying how to solve it. That's a harder problem because a lot of times there are gaps in expertise that need to be overcome. A lot of times there are conceptual revisions that need to be made. Sometimes the constraints are poorly defined of the problem, so it's hard for an artificial system to understand things, whereas a domain expert would know, they'd have an intuition for what would work and what wouldn't. So these are all things that they're kind of considering here in terms of the hard problem. So we can make progress in understanding how humans solve the hard problem by studying the cognitive science of scientists, and then use the results to design new computational agents that automatically infer and update their scientific paradigms. So in this case, it's about kind of understanding how humans solve these hard problems, how experts do this, and then design new computational agents to do this sort of AI scientist type thing. So, they talk about the problem of optimization, the problem with optimization. And so this is where, optimization is great when you already know what the question is. But when you don't know what the question is, then it's harder to sort of lock on to the relevant problems. So this is kind of the basis for this whole idea of the AI scientist. And to do that, you need to go back into the philosophy of science and understand how science is done. And this actually, I like this section because it draws from like Herbert Simon's work, and it draws from Popper and how these things kind of conflict. And then talks about solving the hard problem, where you need to have domain specification and constraint specification. So in domain specification, what are the relevant phenomena that need to be explained by a theory, versus constraint specification, or what kinds of constraints need to be imposed on a theory based on existing knowledge. So these are things that, of course, domain experts can do, not always well, but they do them they do that without generating things that are not relevant or, being able to actually make breakthroughs. whereas AIs really struggle with all this. It's a very interesting article. So that's that special issue. I think it's a great piece of work. Hopefully, hopefully we can dig into it more over the next year, maybe. Any comments or questions?
It's awesome. It's it's an illustrative. It's a great set of papers.
Yeah.
To be a part of. Excuse me. The last paper there, that's the first author is the guy who runs the it's a conference series that is like the foundations of mathematics or something like that.
Okay.
Like it's a really interesting moving conference. It's a conference isn't the right term, or they'll do stuff more than once a year, and they will sometimes be in they'll be in London, then they'll be in Palo Alto, then they'll be in Rome, then they'll be in Split. Or what's the capital? What's the capital of Croatia?
Yeah, maybe something like that. I don't know.
Something. I said Split. I think it's spelled.
Yeah.
Anyway, it looks like Split.
Yeah.
Never been there.
Yeah.
It's one of these things where it's just I could never figure out if they were trying to, were they a startup? Like coming to Silicon Valley, seemed, like fundraising.
Yeah. Yeah.
Maybe that to some extent. I mean, like doing events now, I see you kind of need sponsors.
Right.
Yeah. So hey, if you could get some tech people to sponsor your foundations of mathematics or artificial intelligence or something like that, hey, great, and then do the next one in Rome.
Yeah.
Right, where you and they'll do them in these fancy. I mean, but the set of speakers for them is awesome. I mean, it's not. Yeah. Anyway, it just still reminds me of how cosine would be at a ski resort.
Yeah.
And NeuroSim would do the workshops up at Whistler.
Yeah.
Kind of thing where it's just are we here for the science? Or did somebody just want to pay for their ski trip?
Yeah.
But I'm looking through these, and yeah, this is a good this is a good half year of CogSci meetings.
Yeah.
And yeah, so really, sort of going back to Jesse's point, yeah, where to go from here, or how to go further with some of these, and if that's with the Active Inference Institute, or if that's with connections and threads that overlap there, right?
Yeah.
Because like you said, there's something about there's a lot of cybernetic theory that is just in a different, is contemporaneous with the kinds of things that's in the brain inspired complexity reading group, right? Like these are papers from the 1950s,
Right.
And it's one thing to see. It's one thing to see the roots of modern ideas, like because we would get this a lot at St. John's College, right? Where you're like reading something from hundreds of years ago, and you're like it really seems that this author is prescient and considering these, is like already has a grasp on these bigger problems that won't be solved for hundreds of years.
Right.
But there's the computationally, like actually solving those or creating algorithms that do that do the things that Wiener was talking about, but obviously with computational structures that he had no concept of.
Right. Yeah.
It's just like is this where our language is actually misleading us, or I should say our analogizing is kind of misleading us and not, I'm just thinking of that anyway, and that active inference as to kind of embody it,
Yeah.
that Daniel Friedman is doing, where it's like these inference.
Oh yeah,
right?
yeah.
Like
The
this,
inference.
which is like the most, which is like the coolest update to vehicles.
Right. Yeah.
Excuse me, sorry for I have this problem with my throat, but replicating ant colony behavior with local, active inference agents,
Right.
with swarms of active inference agents, is a, it's just like, it's like a wonderful mashup of so many things that, but is still very, like you could sort of, I don't know if he ever talked to any animal behaviorists, or like E.O. Wilson was still, was still doing his work at this point.
Yeah. Yeah.
I don't know if there was anybody, like if he would even have the threads from biology to be thinking about this. But you know what I mean? When we think about modernizing cybernetic theory,
Yeah.
like how should we approach it, and like how much of it is best really reframed with is best to think about reframing it with new computational structures that permit, you know, a much more diverse and glorious embodiment, you know, like you know, like a much more, yeah, just like it should be 50 years later, it should be very different,
Yeah.
you know. Can you mine that old literature for ideas at this point, or should you be trying to find, you know, what would their modern embodiment actually be, and it might be coming from a different, um, like active inference, which certainly tries to draw from those historic threads, you know, like, but is it like that's where you should be now, like
Yeah,
a
yeah.
cybernetist should be thinking active inference, you know.
Right.
Because I'm just also just trying to think about, like, I mean, there's something I guess I'm also just trying to explain my own particular um, distaste sounds strong, but I'm just going to use it for lack of with like global workspace theory and
Oh yeah.
and things which seem so like almost like 1970s cog sci.
Yeah.
You know, like
Yeah,
like,
yeah.
sure it gave us the mouse and the GUI,
Right.
you know, but like, is that where we should be? Anyway, just some thoughts there in terms of, you know, yeah,
Yeah.
like loving what the Active Inference Institute is trying to do,
Yeah.
and
Yeah, I think we need to like kind of maybe interact more on a very granular, more granular level than we have about some of these things too. I think there are a lot of people there, and of course there are people who interact with the Active Inference Institute and the special issues. So yeah, I think there's a lot there that we could.
I mean, you know, just also like, you know, like the first vehicles, right? Like they weren't even things that Brainberg, you know, like they were just stepping stones, right?
Right.
Like in his book, he was replicating the nervous system,
Right.
right?
But you have to go through
You
all
know,
these.
yeah. He's giving you a thought experiment. Be like, you can get there too, um, and you know, but like, I mean, I've thought about, you know, trying to build those with the electronics lab that's right behind here.
Oh yeah.
You know, but that wouldn't actually be very, you know,
Insightful.
like yeah, right.
Yeah.
You know, and so yeah, just trying to think about what we should be building, and or like what wet lab experiments, or, you know, like, you know, my bias. It's
Right.
like, you know, we should be growing tissue. Yeah, I the yeah, I think I called it anatomical compiler because I really want to be trying to think about something that doesn't exist yet.
Right.
You know, and you know, but it's just like it's just gonna be where I'm putting stuff that I think is useful to get there.
Yeah.
Right. And this is like, is it Richard or
Rashab.
well, I was gonna say like Soleil.
Oh.
What's Soleil's first name?
Oh, Ricard. Oh, you're talking about a different
Ricard.
person. Yeah.
Ricard. He would be Spanish. Yeah, he'd be Ricard. Okay. This is my French background. I'm thinking Richard. Soleil's, you know, open problems and synthetic multicellularity, right?
Oh, yeah.
You know, it is like great. You know, there's a lot of really interesting interesting domains in which multicellularity is you know, becomes a question of collective intelligence, and you know, like, but you can, yeah. Anyway, like I would certainly love to make some of that that new work really grounded in biology, you know.
Yeah.
And and I still think that that there's a lot of Levin work that is accessible that way,
Right.
or sorry, I should say is accessible in as unsophisticated a lab as behind me.
That you can do it on your own, like
well, that's you know, like we got some real ringers in the lab right now.
Yeah.
You know, like they're here. You know, this one postdoc, former postdoc UCSF, like he's here to have a startup, and you know is thinking about ways to, you know, like they're trying to make careers beyond academia,
right.
but they're also coming with some incredible experience and skills, and are happy to contribute those, you know, for such an effort. So anyway, trying to think about how to do that.
Yeah.
We just did an event last night that was pretty awesome with like some principals from Science Corp. Excuse me. So that's the Max Hodak company that's, like, you know, co-founder of Neuralink, who started a company doing biohybrid electrodes. So it's really interesting kind of mashup of cellular biology with you know, neurotech. As well as Andreas Tolius, who runs the Enigma project at Stanford. But it was nice that one of the neurotech at Santa Cruz students was there and said that he would be interested in doing a summer project. That so I'll see if we can be doing some more tissue culture.
Okay.
And like there really are some accessible, like the 3D printing. I think the literature shows there's some really nice. I'd like to connect some of the 3D printing to some of the work that Ricard Soleil talks about.
Yeah.
Anyway.
That's great. Yeah. So yeah, that's great. Thank you for the insights. Like I said, we'll be revisiting this over a long time span. It fits into a lot of things we're talking about in this group. So, yeah. So I think that's it for today. Yeah. Thanks for attending. Yeah, there's Jesse. Actually, maybe Jesse wants to say some parting words. Okay. Yeah. All right. Good stuff. Yeah. Thank you. All right. Yeah. See you next week. Thank you. Bye.
Take care.
Take care.
Thank you.
Thank you.